Okay, so I'll make a start on this. We'll see how we go if anyone else turns up. If not, happy to have a look at where you're currently at. Otherwise, at least for the start, we'll go for the proposed agenda here, which is to essentially review the probability stuff we had a look at. It's going to be basically top to bottom, start a probability, end a probability. It'll be a bit of a mix mash. And I think one of the best ways to go about that is to actually start with the extended response questions. Because one of the things they do interestingly with the probability extended response questions is they, within the same scenario, do their best to basically make their way through all of the possible probability types. So we're looking at stuff like normal distribution, stuff like then binomial, maybe some sampling and estimation will make its way in there. And essentially, you have to be aware of the fact that at any stage from question A to B to C to D, the probability type that you have can change. And that'll usually be denoted by there'll be like a separator between the question. So if we have a look at the screen share, it is on now. Yeah, screen share's on. If we have a look at the screen share, you'll notice question 1, yep, has all the information, makes sense. A and B are back to back. You can be reasonably certain that A and B are both normal distribution questions, considering it said it was normally distributed. You'll then notice there's a spacer between B and C. Suddenly, you've now got a PDF, a probability distribution function in the context of a piecewise. When you have that sort of function, that's an immediate indicator that you've now converted to continuous probability rather than specifically normal distribution. Another separator here will mean a different thing. I'm seeing Lake A and Lake B, possibly binomial. You have two separate outcomes. And so essentially what's happening is, and this is really common in an actual exam, right? In an exam, the tech-free exam is going to have 1 or 2 probability sections, and they're quite long, and they'll do this sort of thing. So let's see how we go. I guess the first thing to really consider, in fact, maybe what I'll do is I'll pull up, I made this so long ago, it's not actually available on any of the school stuff, because I mean, if you look at it, there's like 89 pages in there. And what I had done at some point was just go through, here's literally every key question ever for, for probability. And here's a massive guide you can follow for all those questions. Now, I don't think having all of that is particularly helpful. If you do want to access this, let me know. I'm more than happy to give it to you, but I just don't see it being particularly helpful, except for the first part, which basically gives you a overview of how you can go about solving these kinds of questions. Because fundamentally, you're going to have some sort of background information that's going on, which will be like, it's a fish shop, there's normal distributed stuff, and then there'll be the actual problem statement itself, which will be like section A, section B, that sort of thing. And so pretty much the first thing you want to do once you've identified those key pieces of information is figure out what type of probability you actually have. And I've got a few guidelines as to how to figure that out. Right, here's a few dot points on if you have binomial. Here's a few dot points if you have discrete. If you have normal distribution, PDFs, sample proportions. Basically keywords that come up that might indicate you have one way or the other. And so maybe the first half of this will be interesting to have. I'll just chuck the whole PDF in there. You can chuck it out if you don't want it afterwards. It's fine. But yeah, this are the sorts of things you'd be considering when you go through solving these kinds of questions. Let's give it a shot. We have a fish shop, 2 different lakes, Lake A, Lake B. The weight of trout caught from Lake A is normally distributed with a mean and standard deviation of such and such. Find the probability that a trout caught from Lake A weighs more than 4.25 kilograms, correct to 4 decimal places. Any thoughts on what's going on there?
Not really.
Really? Okay. But one of the first things we can try and figure out is what kind of probability we're working with. So it's pretty much going to be one of the chapters 13 through 14. Do we have discrete? Do we have binomial, continuous, normal, or sampling and estimation? Which one do we have?
It's not discrete.
Not discrete is correct, yeah, not discrete. There's a keyword in there that'll tell you which one.
Is it binomial?
Not quite. So binomial, you'd have to have, I mean, yeah, I see what you mean by like having lake A, lake B. You've got your potential for two possible outcomes. However, it does tell us we're using normal distribution. It is a normally distributed thing. So that means we're going to be doing the chapter 16 stuff, essentially. But okay, so now that we know that we're doing the normal distribution way of solving a thing, the next question becomes, okay, we want to find something, or find the probability that it weighs more than 4.25 kilo. So the question then is, how do we find a range of probabilities when it comes to normal distribution? It's okay if you don't remember it. It is a CAS thing specifically. Do you remember?
Not really.
Not really? That's fine. We're going to do a full review of basically everything right now. So we've done like what, one class on each thing. It's going to be this normal CDF option here. It's going to be the same for the Casio as well. You put a lower bound, you put an upper bound, and you put the mean and standard deviation. So we knew the mean was 3.6, so we put that in there. We knew the standard deviation was 0.5. We know we're looking for greater than 4.25. That means our lower bound is 4.25. And a key nuance of normal distribution is that you put infinity as an upper or lower bound if it's not already capped. Like if this had instead said between 4.25 and 5, then yeah, you would do 4.25 and 5. But if there's no known cap, you put it as an infinity. And so that's pretty much it. You get your number, you truncate it off, sorry, you round it to 4 decimal places. Fair enough?
Yeah.
Sweet. Next up, part B. The probability that a trout caught from Lake A weighs more than some number of kilograms is 0.9. So we don't know the weight, but we do know the probability of that particular thing occurring. And our goal is to figure out what the value of K is. This is another CAS function. It's either going to be 1, 2, or 3. Definitely not going to be 2, because we just use that for a range of probabilities. So that really just sort of boils down to two separate, or two possible things there. So what do we do when we don't know what the, it says K, but we usually think about like as an X value. We don't know that, but we do know probability. Whereas in the previous question, we knew our X, but we didn't know our probability. It's the opposite. Do you remember which one we have to do to solve from there?
Is it the inverse normal?
It's the inverse normal, yeah. Inverse normal. So the keyword area there is going to be the total probability. Now, one thing that's really useful for when you're doing this, if, sorry, what CAS do you have again?
I have the Inspire one.
Inspire, okay, cool. So one thing that needs to be said about this is that the area has to be to the, oh shit, now I've got to remember it, to the left. Yeah, to the left. So what I mean by that is any normal distribution is going to look like this. Right? It's going to have that bell curve look and shape to it. So one of the things that's worth pointing out when you do this is figure out, hey, what does it even mean that more than k is 0.9? Well, basically it means that you've got some k value somewhere, and then everything more than it, so bigger means to the right, that total probability is 0.9. So all of that accounts for 90% of the total area. Weighs more than k kilograms, it's 0.9. When you're doing TI Inspire, it always looks left. So when you put in your area, you don't put 0.9, but you put 0.1 instead. Otherwise, everything else is pretty chill. You put the mean and standard deviation from before. So 3.6 and then 0.5. The result that you get is kilograms. So in this case, we're looking at like, what, 2.96 kilograms for that particular thing. To then verify that, you could then just plug this back in to the normal CDF. So you can say, okay, cool. If I then plug this back in here as my new lower bound, do I get 0.9? And yeah, we get 0.9. That's a nice little way of verifying that you've done it in the right direction. You have a little picture, you think, oh, yep, I know it's got to be left, so I flip it. And then maybe you could do one little check here to make sure, yep, do we still in fact get the 0.9 that we were expecting? Is it fair enough there?
Yeah.
Sweet. Okay, we've got a new section of information before the question, which probably means we're going to change probability types. So I'll let you have a read of that. Have a think about what type we're changing into. So we can rule out normal because we've just done normal.
Wait, sorry, we're looking at C?
We're looking at C, yeah, but there's this new piece of information right before it. So before we do the actual question, it's worth highlighting, hey, what probability type do we have now? Because anytime you have a little division between the sections, probably means the probability type is going to change. So that'll be the first thing to consider. What has it changed to?
I'm not sure.
Not sure, that's fine. So if we have a look at the types, first up is binomial. So do we have two possible outcomes? Or I guess, is this even discrete to begin with, right? So are weights of things usually discrete outcomes?
No.
No, correct. So you can pretty much rule out binomial and discrete, right? Because weights are continuous quantities. So when it comes to continuous, there's only two, sorry, we can even rule out the sampling and estimation stuff because that's also discrete. So now we're just really a 50-50 between doing normal distribution or just regular old probability density functions. We just did normal distribution, so that kind of only gives us one left. And you'll immediately recognize that you have that type of probability because it'll be given by f of x, some function, which is usually a piecewise. We have a piecewise, so sure enough, we're doing continuous in this case. Now, as for executing on the actual question, we want to figure out the mean weight of the fish caught from this particular lake. Out of curiosity, do you remember the calculation for doing mean for continuous?
Not really.
Yeah,
I remember it for binomial, but I don't remember it for continuous.
Yeah, that's fine. It's a very similar thing, by the way. Kind of like how binomial is n times p. For continuous, it's going to be x times f of x. Very similar thing, except you're going to chuck that in an integral. So just because I think we might need it, I'll define it as a function. So h of x is going to be pi over 6 cos pi of a whole bunch of stuff. Cos pi bracket 2x minus 7 over 6. You can put a domain on it from here. I tend not to. I tend to just sort of have domains in where necessary. So for instance, when I'm doing the terminals of my integral, I'll put them in there. And yeah, it's always x times f of x. So you're pretty much just doing x times h of x, and that gives you the mean. Break to 2 decimal places, 3.50. putting in specifically 3.50 would be necessary there because it does say corrected 2 decimal places. It's not often they do that though. Maybe just double check. Did I put it in the right equation? Pi over 6 cos pi 2x minus 7 over 6. Yeah, okay. It's not often they make that happen, but I guess they've done it here. Anyway, next up. Find the probability of a randomly selected trout being weighing greater than 4.25. That's going to be part D there. How do we do a range of probabilities for continuous?
Do we go in menu and then the probability? Is it 5?
TCDF. I don't actually know what this is. TCDF. I feel like this is a physics thing because they've got degrees of freedom in there. But it's not quite that one, no. So when we're talking about continuous probability, we're pretty much doing things exclusively with integrals here. So when we're talking about weight being greater than 4.25 kilo, it just means that our lower bound of the integral is now 4.25 because the integral bounds are your x values, essentially. We're going to get rid of that x times because we're not doing the mean anymore. We're just going to stick with the original function. And because we already know the upper bound is 5, we leave it as 5 there. And so yeah, just hit enter on that. You get some sort of exact value for that. So I guess the main thing I'm looking for here is being able to figure out what kind of probability and what kinds of things we're supposed to be doing. The actual execution of it, I'm sure a lot of it is going to be like, oh shit, I've done so many of them. Which one is it? So I'm not so bothered as like the specific thing to do, but more so like, hey, what's the overall concept? What are we actually trying to achieve? Like, I can notice the phrasing of D is the same as the phrasing of A. In fact, I think they're only differing by a single letter, B instead of A. Oh, randomly selected. So they're basically the same question, is what I'm getting at. You solve one in the normal distribution way, you solve one in the continuous distribution way. Similar thing here. Part E, no, maybe I shouldn't have said that. What is E similar to?
It's similar to B.
Yeah, similar to B, correct. It's got pretty much the exact same wording on it. So now instead of using the inverse normal, because that was a normal distribution, we're essentially doing the equivalent of the inverse continuous in this case. Now, as we kind of highlighted, there isn't really a Cas function for inverse. I guess the challenge is when we have continuous probability that's generic, that's mapped by some function f of x, there's no like inbuilt thing to really look for. So the thing to do here is remembering that continuous means the boundaries of your integral are x values and the outcome of the integral is a probability. So when we're looking at the fact that the probability is 0.9 and we're looking for more than c kilograms, what could we start plugging into our integral? It'll be in a solve, I'll kind of give that one away. What can we start replacing in this integral to start plugging in those terms? Like maybe we'll go one by one. So we got this 0.9 here as a probability. Where does that belong in a solve?
In the front, 0.9 equals.
Yeah, 0.9 equals. Or we can put it in the back, but either way, yeah. That's good. Then lastly, we've got a c value. Where does that belong in the integral?
Wait, sorry, I don't get it. C.
Yeah, that's fine. So C is in kilograms. So think about where does kilograms get represented in just regular old BLX if you have a look back at the actual subject of the question. You know the output of the integral is probability. That's the area under the curve of it. Where does weight appear in our integral?
Isn't it in the domain?
Yeah, in the domain, correct, exactly. That's from 2 to 5 kilo. And you can even figure that out from here as well. We did weight greater than 4.25 last time, which is why 4.25 was in the bottom. Now we're doing weight more than C. So instead of putting 4.25 down there, we'll put C down there. That's it. We're still going to leave 5 as the upper bound because we're not told what a potential upper bound limiter could be. So you just assume it's the maximum. This is where me putting a domain kind of bites me in the ass because I didn't restrict my domain here. So you still would want to put this between... Actually, yeah, maybe I'll ask. What's a good idea to put as a restriction on this so you don't get infinite solutions for C?
Could you have it like do the greater symbol to the 4.25?
25. So 4.25 would be a good idea for the last question because we did have a 4.25 in there. In this case, we are between C and 5. And so definitely the upper bound will be 5 for this. The lower bound, if C is a kilogram, some kilogram value, how low could it potentially be?
0.
Well, let's have a look again at the original function. What's the restrictions on the kilograms there?
Oh, so it would be 2.
Yeah, 2, correct. So the lowest it can possibly be is 2. So we know that our C value is going to be anywhere from, well, 2 to 5. We could probably guess that it's going to be a bit further than 2, but because we're equaling 0.9, it's not going to be that much further from 2. At least I would hope not. You still get some weird exact value. That's fine. Just control enter it. We're supposed to do 2 decimal places anyway. So looking at 2.61, which, as we kind of expect, not too much further from 2, because 0.9 is a big probability. It'd be very unlikely if it was concentrated all at the very end. But yeah, that's that. Next up, I got a bit further information. Fish shop catches 60% of their trout from Lake A and 40 from Lake B. So reminder that Lake A was the normal distributed thing and Lake B was the continuous distributed thing. Part F is then saying, find the probability that a randomly selected trout weighs more than 4 kilogram. Randomly selected trout weighs more than 4 kilogram. Yeah, that's a interesting one. I don't necessarily need the final answer. More so, what would be the things that you consider thinking about on your way to the answer here? Part F.
Would we restrict the domain again?
Restricting domain. Yeah, that'll be definitely part of it, right? Weighing more than 4 kilograms would mean for whatever lake you're doing, it means that your lower bound will be 4 in that case, since you're doing more than 4. Yeah, that's a good start. What else would be things that have to be considered? I don't even think specifically about, like, why did they bother saying this statement here? How does that impact our problem solving? I'll even give a bit of a further hint, which is previously we were talking about trout caught from Lake B, trout caught from Lake A. This just says randomly selected trout. So something about this is going to help us figuring out how we calculate our net probability. Now,
Would we come from Lake A and then Lake B and then add them together?
yep, Lake A, Lake B, and add them together. What about these numbers? How do those make an entrance in there? It might have cut out at the start. I didn't quite hear the full thing. How do we then put these numbers into it?
Would we add it to the integral?
That's the integral. Yeah, so you can put it into the integral. Yeah. The question becomes how to put it in there. So I guess first I'll set it up, which is the integral will be, so 4 as a lower bound, definitely. Where is, so I guess 60% or 40%, which one's going to actually apply to the integral? How do we know which one?
Would it be like would it be 40%?
Yeah, that's it. 40%, because Lake B is depicted by the integral. So we're going to be using 40% on this. Yeah. Now the next follow-on question is, where does 40% make an appearance in this particular function? Or just anywhere on this integral, really?
Could we have it like times it outside of it?
That's it. Yeah, times it. Whether you do it at the front or the back, it's whatever. Yes, 0.4, because it is a, basically we're saying that 60% come from one, 40% come from the other. It's effectively weighting the probabilities of where these trout are coming from. So you take the raw probability of getting it from this particular trout, but because it only is proportionally 40% of the total, we have to now consider that as part of our final calculation. We're going to do the exact same thing with the normal distribution, right? So we got 0.6, which means we're going to do 0.6 times the normal distribution, which I'm just going to copy from up here. Yeah, normal CDF. Mean and standard deviation are already there. Upper bound still going to be infinity. Lower bound still going to be, well, now going to be 4. Yeah, 0.6 times it. That's going to be that. And then as you said at the beginning, yes, you then add those two things together. This plus 0.1 and so 3 decimal places, so we're looking at 0.227. Cool. Make enough sense, that one?
Yeah.
Sweet. Part G, find the probability that a randomly selected trout which weighs more than 4 kilograms was caught in Lake A. That's a cheeky phrasing. How dare they? There's a very specific concept that is brought up in the phrasing of this. They did their best to mask it. I'm curious if you spotted it anyway. There's a specific kind of probability that's being mentioned from this statement. And I'm not talking about like binomial discrete or anything like that. It's still definitely going to be the same sort of thing where we're splitting it between normal and continuous. It's more so like from a fundamentals perspective, what's been discussed here.
Um, we haven't been given Lake A's probability, like density, or we wouldn't need it.
Well, we'll need it, but Lake A was the normal distribution. That's what that one was. It's more so in the phrasing here. Randomly selected trout, which weighs more than 4 kilograms, was caught in Lake A. It's a very... Do you want to have a think any more about it, or should I just give this one away? It's a bit of a weird phrasing.
You can say it.
Yeah, okay. So this one's actually conditional probability. Normally we think about the word given, but fundamentally conditional probability just means find probability of something given that we know something else has already occurred. So the phrasing of this is such that you want to find the probability of being caught in Lake A, but we already know ahead of time that it was 4 kilo. So it's actually a conditional probability. 90% of the time they'll say the word given and they'll make it quite obvious it's conditional probability. This time they decided to be cheeky with it. But okay. So let's see. So when it comes to conditional probability, if we ignore literally whatever, like normal, continuous, whatever, do you remember the equation for conditional probability?
Is it on top the union of both of them?
Pretty close to the union. What's the other thing instead of union?
Or?
Well, oh, maybe you just don't remember the terms. Or is union. Intersection is and.
Intersection.
Yeah, so looking for intersection, that one. Yeah. But okay, so what are we actually doing here? This is the probability of Lake A. So we'll say probability of A given it was more than 4 kilo. So let's say weight more than 4 kilo. It's going to be the intersection of those two things. So A intersecting W greater than 4 kilo. What do we put on the division? What goes on the bottom?
The thing after the straight line.
That's it, yeah. Weight greater than 4 kilo. So just by looking at that, we actually already know one of these probabilities. We calculated it earlier. Which of these do we know?
The bottom?
Bottom, yeah, correct. We already calculated that in part F. So all that's left now is figuring out what our numerator is, and then we can just do a quick division. So A intersection weight greater than 4. That's a fun one. I've got an idea how I could calculate that, but I'm open to suggestions. What comes to mind when trying to calculate an intersection?
What they have in common?
Yeah, what they have in common? Absolutely. Like A and greater than 4 kilogram. We have that one as well, actually. The intersection of like A. Now this is going to get a bit tricky because I can think of two ways of doing this. One is tree diagram type, where you can go between Lake A, Lake B, have a certain probability of being selected. That's going to be 0.6 and 0.4 respectively. So it was 0.6 Lake A and it was 0.4 Lake B. And then you've got from there, the weight is either greater than 4 or less than 4 for both of those. Greater than 4 kilo, less than 4 kilo. This would have to be the correct way of doing that because it takes into consideration this earlier bit here, which is that the probabilities are weighted a little bit. Because before thinking about tree diagrams, I was kind of thinking, well, okay, A intersection weight greater than 4 just means when we calculated weight being greater than 4 for normal distribution. But the fallacy in that is that's actually a conditional probability. Right, like if we just use the answer from part, where was it? Did we even do one? If part A had said 4 kilo, what we would have actually calculated would have been probability of 4 kilo given Lake A, because it came from Lake A. It's not actually an intersection. So when we think intersections, better thinking things in terms of tree diagrams. Think about the procedure going from A or B to being greater than or less than 4 kilo. Now, granted, we do know this one, or at least we could quickly find it. It was Lake A, so that's the normal distribution. So pretty much we're just going to take the normal distribution that we found from earlier. Wait, that's just it, isn't it? That's the whole thing. Because if you take away the 0.6, you can get your calculation, sure, but you are just going to multiply it by 0.6 anyway. It's going to get you 0.211, which you'll put here, 0.211. But to find the intersection at the end, you're just going to multiply it by 0.6 anyway. So I guess we actually had both. We did have our intersection when we did calculate it the first time, which was this number. And then what we said earlier was we had our denominator, which was just greater than 4 kilo, which was this thing. So final answer, 55.9 or 56%. I guess it's 3 decimal places. What are we doing here? So 560. Yeah, 0.560. It's a bit of a exploration there. Was it fair enough what was going on? If you said something, you were muted.
Yeah, sorry. Yeah, it makes sense.
Yeah, cool. Yeah, cool. Good one. These are typically long questions. They try to basically fit in at least 3 different kinds of probability into the same question. Like in part H. H is a bit sneaky because the probability does change here, but they didn't sort of use a separator. They try to slide it in a bit. Like if you read H, you've now got fish that is combined into boxes of 6 for distribution. So now they very specifically said boxes of 6. Now we're probably thinking things like discrete, right? It's in boxes of things. And so these trout that we found from earlier came from different places, had different probabilities of being whatevers. They're now in boxes of 6, and we want to figure out, okay, cool. We got this box now. I want to figure out what's the likelihood that at least one of the trout in a box weighs more than 4 kilo. So I've got 6 in total. Any number of trout from 1 to 6, at least one of them should have a weight of more than 4 kilo. Kind of gave it away in the context of it being discrete, but there is one final decision to make, which is what kind of discrete? Do we have just plain old regular discrete, or do we have binomial in this case? What's the difference?
Would it be binomial?
That is correct, binomial, yeah. Why?
Because it's saying at least one trout in randomly chosen.
Okay. That statement could apply to either of the discrete or binomial. I'll pull up the criteria for binomial again. Let me know why, based on having a look at that, what would inform decision for binomial.
Repeated trials?
Yeah, repeated trials are independent. So we figured out earlier that the basic probability of getting a trout greater than 4 kilo was calculated in, where was it? Yeah, F. So if we just look broadly speaking, any random trout being more than 4 kilo is going to be calculated by the answer of part F. And so when you now have a box of 6 of those random trout, then yeah, each repeated trial is going to be independent because any given trout is going to be subject to that same probability. That's good. The other and probably more important one that could be an immediate yes is that it's actually binomial because you have 2 possible outcomes. It's either greater than 4 kilo or it's not greater than 4 kilo. That's the bigger thing to consider in the context of binomial. It's all required, but if there's going to be one criteria that you memorize for binomial, it's going to be 2 outcomes. So we know it's binomial. How do we find binomial probabilities? Specifically in the context of saying at least one means you want to have like anywhere between 1, 2, 3, 4, 5, or 6. Do you remember how we find that kind of thing on the CAS?
Yeah. Do we go to binomial PDF?
Binomial PDF. All right, I'll show you what that one looks like.
Sorry, no, CDF. CDF.
Yep, that's good. Let's just be cool. All right, how do we populate this?
So n will be 6.
N will be 6. Yep. We'll leave that as a whatever. We'll pull the actual probability from part F.
The lower bound will be 1.
Yep.
And then the upper bound will be 6.
Sounds good to me. Cool. So we'll just get that on the paper, and then we'll grab a copy of this, delete the little placeholder, and then try to remember how we did the other one, which I believe would have been this, because we did our integral, we did our normal, and then we added them together. That will be the probability. I'll just double check I pulled the right one from that. P is 0.227, P is 0.2, yeah, cool. Yeah, that's it. Sorted. 0.79 if you round to 2 decimal places. Nice. Okay, lastly, I won't even say anything for I. I'll see if you can spot what's, maybe at least just have a walkthrough as to what's different here, what you might start considering.
Could we put it in algebra solve?
Algebra solve? Yeah, probably. At some point, I could imagine, a CAS solve will work. Yeah. So part of the challenge of that is figuring out how to get an equation into the CAS solve. So what kinds of things will we consider in creating our equation for that?
Would we look at the value of n?
Value of n. Yes, it'll be like a comma n sort of situation. You're solving for n, absolutely. We need an equation with n in it, then. That makes sense. So how could we potentially create that equation?
Could we replace the 1 over n over 1 over 6?
N being 6. Okay, cool. N is a redefining of the boxes of the size of the box. So we're essentially overriding this previous information where the boxes were 6. In this case, they're boxes of n. So putting n back in as 6, not particularly doable because this has overwritten that previous information. So, I mean, good idea that you were spotting like n was 6 last time, so n6 here should be good. Not quite doable though because it does overwrite that. What else could we potentially be considering? What is this p hat? What's this hat really indicate? What area of study does that show up in?
I've never seen that before.
Oh, right, okay. Maybe you weren't here for the last class then. Did you do any sampling and estimation stuff?
No.
Yeah, okay, cool. Then, okay. So that's the sampling and estimation chapter, where essentially this is still a discrete kind of thing, but the only thing you have to do is try to convert your p hat values into x values like we're used to. And that sounds probably easier than it actually is. Sorry, that sounds harder than it actually is. What I'll do is I'll pull up a PDF that sort of walks through what the actual difference is here. So p hat basically means we're thinking about things in terms of proportions rather than in terms of raw values. So for instance, if I have 4 white and 6 black balls, that's the number of each of those, right? I have x equals 4 for 4 white balls. Alternatively, I have a proportion of 4 out of 6 in terms of, 4 out of 10, because it totals to 10 of white. So whether I say 4 white balls or 4 out of 10 as a proportion, we're talking about the exact same thing. One's written as a percentage, or fraction rather, and the other's written as the raw x value that was underlying it. So basically any p hat is always x divided by n, where x is a number, in this case 4 white balls, and n is a total, in this case 10 total. So when we're trying to calculate p hat equals a third, that means that out of 3 balls that were drawn, so n equals 3, one of them was a white ball, since p hat is the proportion of white balls. So you just go, okay, cool, I got this nasty whatever. Really, it just means find x equals 1 from discrete. So when we look at this one here, this whole p hat being less than 1 over n, yeah, okay, being less than 1 over n, basically you're looking for, that's a bit trickier. I'll show you, I'll try to show you what it looks like mathematically speaking, and then I'll compare it to the previous one and it should make a bit more sense. So any p hat value is always x divided by n, right? So if we have a specific p hat value of 1 over n, well, just by observation, we don't know what n is, but we definitely know that x equals 1. And so to rewrite this as an equivalent x equation, you would call it PRx is less than 1, because you're writing it in terms of x rather than the p hat value. Is that fair enough?
Yeah.
Okay, cool. Now, specifically, we're trying to still solve for n, and that's probably a bit weird considering we look like we've gotten rid of n from this. And we're solving n under the condition that this probability itself is less than 0.1. So it could be like 0.05 as a total probability, whatever it could be. Find the least value of n. So now that we know this is discrete, well, it was actually just sort of masquerading as the, I lost my train of thought there. Basically, it's discrete under the hood, specifically binomial under the hood, because really the only thing that's changed is they said n instead of 6. Everything else is still identical in the scenario. The question now becomes, how do we calculate binomial probabilities x less than 1? How do we normally do that?
You use CDF?
Use CDF, yeah, exactly. We use CDF, which means we need a lower bound and upper bound. So basically, menu 55B, number of trials is n, right? That's where the n's going to come back into it. Probability of success, I'll put a placeholder because we need to copy that from later. Lower bound and upper bound, well, if I pull this back in there, and if you refer back to the information in I, what's lower and upper bound in this case?
Lower bound would be 4.
Lower bound would be 4. I have actually just realized something weird, which is x less than 1 actually just means x equals 0, because it's not an inclusive. So Yeah, if you think about like the number line, because it can't go lower than 0, right? 0 position at all. You got 0, 1, 2, up until n. X less than 1 actually just means this. Okay, cool. So we can actually go even simpler. Now that we know it's a specific value, we got the PDF. Sorry, I didn't realize that until just then. So we've now got n in that spot, placeholder p, oops, can't do 2 decimal places, and x equals 0. Now that's going to obviously spit out garbage because I haven't given it an actual n. This might work. Let's see. Sometimes it does, sometimes it doesn't. We just grab that. We delete the placeholder probability and then put in the actual probability, which is this one. And if you recall, we needed it to be less than 0.1, and we're solving for n. Might work, might not. Nah, it didn't do it. Okay, so we can't necessarily use the cas function for that. How do we do x equals 0 by hand? How do we do that in binomial?
You do the you put it over like the upper bound and the lower bound over, and then you go the probability of like to the power of x.
Yeah, okay, cool, you remember. So it's that whole like nasty long equation that you're depicting.
Yeah.
That's called the Bernoulli sequence, by the way. So you'd have probability x equals 0 is the same thing as, so n is still n, you got n factorial on n take r, where r is 0, and then once again you got r, you got p, which I'll keep as p because I don't want to write out that full decimal, power 0 because you're choosing so you're choosing 0 of those, and then 1 minus p to the power of n minus 0. Now, this always just simplifies down to 1. Hang on, does it? Yeah, n factorial, yeah, that cancels down to just 1. P to 0 also cancels down to 1. So you're left with 1 minus p to the power of n, which does not cancel. That is the same thing as x equals 0. So basically, instead of using the cas function, which, there's all sorts of stuff going on under the hood that would break this kind of thing, instead of having this nice cas, well, I say nice in quotes, cas function, better instead to take the bit that we need, which is, it was 1 minus p, so we want 1 minus that. And we want to raise that to the power of n, so I guess we'll just get rid of this bit. And the comma. So 1 minus p to the power of n has to be less than 0.1, and that's going to give us what we need. So the reason we had to do that is because the cas inbuilt function doesn't necessarily play nice to solve. Sometimes it works, sometimes it doesn't. Is it fair enough why this is a suitable alternative?
Yeah.
Okay. So there's only one final thing to consider here, which is we got a decimal n. What's wrong with that? How can we fix that up?
Can we round it?
Round it is correct. How do you round it?
Would it just be 8?
Just be 8. N has to be greater than 8.9. So it's not going to be 8 in this case, it's going to be 9. Not because you want to round up just because it says 8.9, but more so because of what we did in the cas solve. Like what we just told the cas to do was say, hey, figure out the value of n, or the last possible point for which it will always be less than 0.1. And cas said, okay, as long as your n value is greater than this, you will be less than 0.1. So that means I would round on the upswing rather than a downswing. And if you don't remember that in the actual exam, you do have a fallback, which is, well, again, you've got to copy this particular probability, so I'll just do that ahead of time. And you can actually just test both your values a bit. So you can go, okay, cool. I'm going to go through and do my what are we actually doing here? Yeah, still just x equals 0. So we'll do our n equals 8 as a possible tester. Control V for probability, x equals 0, and you just see, hey, did we get what we wanted? Is that less than 0.1? No. Cool. So now we test the other thing. Should we have rounded up instead? We test it, we got 0.09. That's better, because now we're guaranteeing that it's less than 0.1 as per the question. Fair enough on the fallback strategy there?
Yeah.
Sweet. This is, unfortunately, the kind of thing that is done in literally every tech-free exam. There'll be some section on it. It'll probably go about as long as this. They'll test probably 3 different. In fact, how many did we do here? We did binomial, we did sampling, we did normal, we did. Yeah, okay, we did them all. So they really do try to jam pack everything into the same question because they're trying to test all the types of probability. You'll at least get one of each, it would seem. That's the kind of thing to expect. And there's a bunch of questions in here that'll help you out with that. And there's also literally every single paper ever written by VCAR because they all look the same. Oh, Jesus, so many. It's still going. Up to 15. Oh my God. Anyway, that's about it for today. If there's anything you'd like me to clarify at the end, feel free to let me know. Otherwise, enjoy the rest of your day.
Thank you.
Take care.